Hello everyone. In today's lesson, we're going to be going over the geometric probability distribution, which is another one of our discrete probability distributions. So previously, we looked at binomial probability distribution, which had a couple of things that needed to be true in order to use it. For example, we had n set number of trials. Each trial had two possible outcomes, true or false, heads or tails, left or right, something like that. There was a probability of success that did not change between trials, which of course meant that there was a trial of failure, which also did not change between trials. And in our binomial, we had our random variable, which could be equal to 0, 1, 2 through n. So now we're going to be looking at a slightly different problem. Instead of saying if I have n number of trials and I want to look at the probability of some number of successes, the geometric distribution will allow us to look at if I have some probability of success, what is the probability that I get my first success on some nth trial? Which means that for geometric, we're going to have a slightly different random variable. For the geometric, our random variable first of all, begins at 1. And this is because we can't have our first success on the 0th turn. It has to be starting at the first turn, or it could be the first success on the second, or it could be our first success on the third or the fourth. And because of this, it actually goes on to any number, right? This is countably infinite because you could have your first success on the millionth turn, the trillionth turn, the quadrillionth turn. So the possible outcomes for our random variable that we can find a probability for are a little bit different. But it does still have some similarities with our binomial probability distribution. For example, while we don't have a set n for this problem, because this is actually what we're solving the probability for, probability of the nth turn being our first success, we do still have a set and unchanging p, which of course means that similarly we have q, and each trial also has two possible outcomes. So it still has that sort of binomial outcome for each trial. And what we're looking at is, right, success, failure, heads or tails, things like that. So an example of using a geometric distribution might be something like saying that I have a weighted coin with a 0.2 probability of flipping a head. What is the probability that I get my first head on the fourth flip? Something like that. So for our geometric probability distribution, our probability that our first success will be on some nth turn is going to be the probability of success times the probability of failure to the n minus 1 power. And this is kind of the same thing that we did when we were doing a binomial probability distribution. We have the number of failures to get up to having that first success. So if I have my first success on the 6th turn, that would be the same thing as saying that I have 5 failures. And of course, if we want to know the probability of that occurring, we would take the probability of getting a failure times probability of getting a failure times probability of getting a failure times probability of getting a failure. And then finally, we get our success on the 6th turn, which means that it would be times probability of success, which could of course be rewritten instead as q to the 5th power times p. So basically, no matter what step you want your first success to be on, your number of failures would have to then be n minus 1. So if I said, what's the probability of getting my first success on the 10th turn, that means that I would have to have 9 failures in order to get there. Because the thing with the geometric probability distribution is, once you have your first success, it stops. Meaning that if I say that my first success is on the 10th trial, that means I could not have had a success on the first or the second or the third or the fourth or any trial up until the 10th trial. Now with the binomial probability distribution, we also had some ways that we could find the mean, variance, and standard deviation, which really simplified things from our general case for discrete probability distribution where we'd have to know every possible probability. So for the geometric probability distribution, our expected value of x, which is equal to our mean, is just equal to 1 over p, or 1 over the probability of success. So going back to my example I brought up, where I had a weighted coin, and I had a 0.2 probability of getting ahead. This means that if I were to find the expected value, I would expect how many flips before I get my first head on average? Well, it would just be 1 over 0.2, which would give us 5. So if I have a 20% chance in any given flip of flipping ahead, I would expect on average it takes me 5 flips, right? So this means that in any given experiment, I might get it on my first turn, or my second, or my third, or my fourth, or my fifth, my sixth, my seventh, my eighth, my 10th, the 20th. But on average, it'll take 5 flips in order to get my first head. Now, the variance, sigma squared, can be found with 1 minus p over p squared. And then the standard deviation is just the square root of this. So if we take our standard deviation, sigma, this will be equal to, I'm going to take the square root of the whole thing, so 1 minus p over p squared. Now, when I have the square root of a fraction, I can actually split it to the square root of the numerator divided by the square root of the denominator. So this is going to be the square root of 1 minus p over the square root of p squared. Well, the square root and the square are going to cancel in the bottom, and we're just left with the square root of 1 minus p divided by p. So we've got our expected value, 1 over p. We have our variance, 1 minus p over p squared. And we have our standard deviation, the square root of 1 minus p over p. Let's do some examples to test this out. Consider a deck of cards. Select a card randomly without looking, note down which card is drawn, and then replace the card to the deck and then shuffle the deck back up. Then what we're interested in is the number of cards we must draw in order to be sure that we have a picture card. Now, one thing that is actually kind of important about this problem is the fact that it brings up that we put the card back into the deck of cards. This is because, remember, our probability P cannot change. So if I were to take that card, look at it, and then put it aside, I've now changed the probability of success on the next draw. So in order to do a geometric problem, it does assume that the probability does not change. Therefore, we would have to put the card back in the deck. So we're looking for a face card. So the first thing we're going to do is let's write down our information that we know. Our probability of success, which would be the probability of getting a face card, is the number of face cards divided by the number of our sample space. Well, there are 3 face cards for each suit, Jack, Queen, and King. There's 4 suits, meaning that we have a total of 12 face cards. There are 52 cards in the entire deck, so this means that we have a probability of success of about 0.231. Now, because we have this probability of success of 0.231, we know the probability of not getting a face card, which would be our probability of failure, would be 1, the entire probability of the system, minus the probability of getting a face card, so 1 minus 0.231, which would give us a probability of 0.769. So from this, we can now find our probability of getting our first face card on the 4th attempt. So we want to find out what is the probability that our first face card is on the 4th draw. So this is just going to be the probability of success, 0.231, times the probability of failure, 0.769, to the n minus 1 power. So n in this case is 4, so this is going to be to the 3rd power, right? Because our probability formula is probability of n equals the probability of success times the probability of failure to the n minus 1 power. So this is going to give us a probability of 0.105. The next part of the problem asks us to find the expected value and the variance for this problem. So the expected value is just going to be 1 over p. So in this case, it would be 1 divided by 0.231. Or if you wanted to, you could actually convert this and use a fraction to solve this. But in this case, it would just be equal to 4.333. Okay, so what does this mean? It means that if I were to draw cards, look at them, put them back in until I get a face card, on average, if I did this many times, many repeated trials, I would expect about a little over 4 draws before I see my first face card. Okay, so now for variance, we have sigma squared equals 1 minus p over p squared, and we just plug in our p. So we get 1 minus 0.231 divided by 0.231 squared. And this is going to be equal to 14.44. And if we want to take it one step further and find the variance, we could just take this value and take the square root of it, because the standard deviation is just the square root of the variance. So this is going to be equal to the square root of 14.44, which is going to be equal to about 3.8. Our next example says that a bulb manufacturing company finds that 1 in every 50 bulbs produced is faulty. So this is going to be our probability of finding a faulty bulb, 1 out of 50. What is the probability the first faulty bulb is the 8th bulb produced? So in this case, the first part of the problem is asking us for what is the probability that our first faulty bulb, if we were to go through and check bulbs, would be on the 8th bulb that's produced. And in this case, we had a probability of finding a faulty bulb being 1 over 50, which is equal to 0.02. So then just plugging into our formula, which is probability of finding a fault on our nth turn, would be the probability of success times the probability of failure to the n minus 1. So in this case, our probability of finding a faulty bulb is 0.02, which means that our probability of not finding a faulty bulb would be 1 minus 0.02, or in this case, 0.98, to the 8 minus 1 power. So rewriting this, we get 0.02 times 0.98 to the 7th power. And this would give us a probability of 0.02. This means that the probability that we would find a faulty bulb on our 8th bulb, being the first faulty bulb, is only 0.02. The second part of the problem asks, what is the probability that the first faulty bulb is the first, third, or 5th bulb? So in this case, we want to know what is the probability our first faulty bulb is the first, or the third, or the 5th. Now notice that I wrote this using unions. This is an or statement because we would consider this acceptable if it was on the first bulb, or if it was our third bulb, or if it was our 5th bulb. It's not asking about it being the first faulty on the first and third and 5th, right? You can't have a bulb that the first faulty bulb be on the first turn and on the third turn, but you can with an or statement. So we will accept if finding a faulty bulb on the first turn, or the third bulb we check, or the 5th bulb we check. So in this case, it is just going to be the probability of finding it on our first bulb we check, plus the probability of finding it on the third bulb we check, plus the probability of our first fault being on the 5th bulb we check. Now, if you remember from our inclusion-exclusion principle, then we would need to subtract out the intersections of 1 and 3, 1 and 5, 3 and 5. We would then need to add in the intersections of 1 and 3 and 5. But the thing is, these are mutually exclusive. As we discussed, you cannot have the first faulty bulb be on the first and also the third term. This equals 0 because this would be the empty set. It's not a possible event. So therefore, these are mutually exclusive. So all we have to do is find the probability of each one, add them up, and we're done. So the probability of getting our first faulty bulb on the first turn is the probability of success, which was 0.02, times the probability of failure, 0.98, to the n minus 1. Well, n in this case is 1, so we get to the 1 minus 1 power, or the 0 power. So of course, this is going to just become 1, and this first term is 0.02. Plus, now we're doing the probability of our first faulty bulb being on our third turn. This is going to be the probability of success, 0.02, times the probability of failure, 0.98, to the n minus 1. 3 minus 1 gives us squared. And then probability for the 5th turn would be 0.02 times 0.98 to the 5 minus 1 equals 4 power. So doing all this, we would get a value of 0.058. The next problem asks us, what is the probability that none of the first bulbs are faulty? Now this one is a tricky one because if you tried to do this using the geometric, you might think, okay, well, I get my first success on the 9th trial. But it doesn't actually say that. It just says that the first 8 bulbs are faulty. So this is kind of going back to the logic we looked at when we first started looking at how we build out a geometric distribution, which would just be the probability of getting 8 not faulty bulbs would be the probability of getting not a faulty bulb on your first try, and your second trial, and your third, and your fourth, and your fifth. So it would end up being probability of not finding a fault to the 8th power. So in this case, it would be 0.851, which kind of makes sense if you think about the fact that we have a very low probability of finding a fault. So it makes sense that 85% of the time, we don't expect to find a fault in our first 8 bulbs. Okay, the last problem asks, what is the variance of the faulty bulbs? So if we wanted to find the variance for these faulty bulbs, variance is sigma squared. This is going to be equal to 1 minus p over p squared. And then again, we just plug in our values. This is going to be 1 minus 0.02 divided by 0.02 squared. Of course, 1 minus 0.02 is just your probability of failure. So actually, you could think of this, if you wanted to, as q over p squared. But regardless, this gives us 2,450. Now, we've talked about this before. Standard deviation and variance, both are ways of measuring how much variation or deviation there is in our data. But because we square our terms to get to the variance, a lot of times it's easier to actually kind of understand what it means if we were to look at it in terms of standard deviation, where we take the square root to get it back into the scale that our data started in. So I'm going to do just that. I'm going to take the square root of 2,450, and this is going to give me 49.4975. So what does this all mean together then? Well, if you look at our probability of success, 1 over p would be our expected value. So 1 over 50 would just be an expected value of 50. Meaning that on average, if we have a 1 in 50 chance of finding a faulty bulb, we would expect it to be about 50 bulbs before we find our first faulty bulb. Our standard deviation tells us with a standard deviation of about 50, meaning that any value from 1 to 100, perfectly reasonable, exactly what we would expect. The further you get beyond 100, because obviously we can't go below 1, the less likely it is. So chances are, if you find a faulty bulb for your first time in the first through like 100th trial, that's perfectly normal. As you go beyond that, let's say you go out 2 standard deviations, so that'd be up to 150 bulbs. Okay, that's a little less common, but still pretty fine. If you go out 3 standard deviations, right, so this would be 50 plus 150 would be 200 bulbs that are before you get your first faulty bulb. That's starting to get into that very unlikely territory. Can it happen? Yes, but it definitely becomes a lot less likely. So this is kind of how it all fits together. And this is really all there is to the geometric probability distribution. It's pretty simple, it's pretty straightforward. The only value you need for it is p, because we don't need our number of n trials, because that's something we're actually solving for. And that's it. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.